Thank you for being here, despite this being the last, but hopefully not least, talk of the day. So I'm Moritz and not Tim, and I'll be presenting GRIMOIRE, synthesizing structure while fuzzing. So for this talk, we have one overarching goal, and that is the one of finding bugs in programs you can see here, in programs that expect the input to be of a very specific structure, right? We have a few interpreters, a compiler. The input must have a very specific structure. So we're on the fuzzing track. What do you expect? We're going to use fuzzing to hit that. In a first, maybe somewhat naive attempt, we could be using blind fuzzing. So basically, we just feed some input to the program and monitor the runtime behavior, right? Now we can consider an abstract view of some arbitrary program, or rather its state space. So in the dark shaded areas, in the dark gray, you can see interesting areas. So an interesting area is for us the stuff that is deep beneath the surface of the program, where the interesting logic is happening, while the uninteresting area in white might be some early states, so before some check. And as you can see, for blind fuzzing, we are hitting rather random. The black point is the seed, and the small X's around them are mutations. So we are moving, but we are not really moving anywhere far from those inputs. The logical question is obviously, can we do better? And I guess I'm not spoiling anyone in here when saying, yeah, coverage-guided fuzzing will help us. So we add program instrumentation to the equation. Basically, we instrument the program with the goal of having a feedback path so that we know which coverage is achieved by a single input. So for each input, we can see whether it achieved new coverage, it found something new, juicy, interesting that we didn't see before, and if that is the case, we want to keep that input. However, if we, by some mutation, create another input that achieves exactly the same coverage, we are not interested in that one, so we'll discard this one. So that's basically coverage-guided fuzzing. I used mutation in here. So let's take a quick look at the type of mutations we are talking about here. So we are talking about bit flips, about simple arithmetic where we add or subtract some constant. But our mutation could be the setting of some interesting value. Maybe we set a byte to 0. We might have a havoc stage where we non-deterministically apply various random mutations, or we repeat some input, or also we can splice two inputs together. So these are different mutation operations. However, they have all one property that is valid for all of them. So they are only modifying a small part of the input. So they are rather local in nature, and that's why we will refer them to as small-scale mutations for this talk. These mutations work quite well for a lot of inputs. So we might have a program expecting an input that looks like this one, numbers, bytes, whatever. And if we apply our mutation here, it might look like this. And I guess it's still valid, right? It looks good for us. So back to our abstract view, these coverage-guided mutations allow us to move and to discover other interesting areas in the state space. As you can see, we have these arrows allowing us, these arrows that are mutations, coverage-guided mutations, that allow us to even cross small gaps between such interesting areas. And we discover quite a lot here. However, you notice in the bottom right hand of the figure, there's a small island that is interesting, but we do miss it. Still, I would claim we covered quite a lot of the interesting stuff here, right? So the problem here is that not all programs are equal. We might have other programs that take inputs that look largely diverse, so something like that maybe. So coincidentally, that looks close to inputs that programs take that we are interested in, if you remember the first slide. And if we do use our small-scale mutations here, so flipping a few bits, adding constant values, it might come close to something like that. But that doesn't look like a good input, right? that's not looking really valid. That's not what we want in this case. So what's the takeaway from this? For this program, we need to know the input structure so that we can apply reasonable mutations, right? So if we hop back to our abstract representation, this program expecting this different input might look like that. You immediately notice there are way larger gaps between the interesting islands, right? And our coverage-guided small-scale mutations are not reaching anything meaningful. I mean, like, there are 2 islands close, okay, we see that, but we miss a lot of stuff. So the question here really is, how do we cross these large gaps? And fortunately for us, that's kind of a solved problem. People came up with grammar-based fuzzing. So you can specify a grammar, a formal specification, and give that to the fuzzer, so that the fuzzer is capable of crossing these large gaps, because now it has access to the input structure. That's cool. Looks good, right? We hit everything here. So what's the problem? Why am I still talking? The problem is that such a grammar requires human effort. And that's exactly what we want to avoid, right? We want fuzzing to be a highly automated process. We want to make it accessible to a lot of people, to developers, and we don't want to have a human being, maybe some expert. We don't want to require domain knowledge in this case. So that's where our paper starts. Our intention is to have an approach that crosses these large gaps in the state space, so that applies large-scale mutations that modify the input to some large extent without requiring a grammar that is specified by a human being. So basically, GRIMOIRE, as our approach is called, learns the structure of the inputs during it is fuzzing. And with this learned knowledge, we then can apply large-scale mutations to cross these large gaps and hopefully profit from that. So the question here is, how do you learn structure while fuzzing? To this end, we employ a process that we dubbed input generalization. So assume an input that might look like this: pprint AA. And what we want to know about this input is whether it contains elements, parts of it, that we can safely discard. To this end, we split the input. We have various rules of splitting. For this example, we split it into blocks of 2 characters, might be blocks of 4. And then what we try is, we try to remove every input from this block and then feed the rest to the fuzzer. So let me walk you through this example. We remove the PP, so we end up with having rint AAA as the rest. Then we send this to the fuzzer and look what is the new coverage achieved by this input. And the fuzzer tells us that is not the same new coverage that the original input achieved. This means the PP was actually relevant to the input, so we cannot remove it. Intuitively, that might be clear in this example because pprint is a valid function and rint doesn't look like, right? So with that knowledge gained, we do keep the PP. We go to the next element. We try removing Ri, ask the fuzzer again, and still we need this element. We can continue with NT, with the space and apostrophe. It's all the same, we do need to keep them. However, when it comes to the AA, it gets interesting, right? As we can see here, the fuzzer suddenly says, this is exactly the same new coverage as our original input. This means it does not matter whether we send our original input into a fuzzer or this one without the AA, which is quite cool because we just learned we do not need this block. So we do remove it, but we remember where we removed it and what looks like there's a missing Unicode character, is actually our symbol for a gap. So here we remember that we removed something. Okay, continuing with the next block, we also can remove the second AA, obviously. And the last apostrophe is needed again. So after merging adjacent gaps, we do end up with something like that. We have pprint of some gap. So we learn from this original input that we can discard everything between the apostrophes, which is marked by the gap, which is quite cool. Let me show a second example before we see why this is cool. We might split this input on white spaces. That's just a different rule we apply. And ask the fuzzer for every part again. The fuzzer then helps us learn that we can discard the white space between the bracket and the then, and we can actually discard the x equals 3 between the then and the end. So now we have different inputs, generalized inputs, and why is this cool? What can we do with this? Intuitively, this is cool because now we can simply pick an input. We can select some arbitrary gap in this input, and we can just insert something. And this is a different input, right? So what we just did, we mutated, but relied on our knowledge of the underlying structure. So let me show what the actual mutations we use are. The first mutation operation we do use is the input extension. Basically, for two generalized inputs, we can concat them. There are two possibilities, so we can first have the pprint and the x equals y after it, or the other way around. So this mutation is inspired by the insight that highly structured inputs often consist out of a chain of valid, syntactically correct statements. So think of statements in a C program that are separated by a semicolon, right? The next mutation we do use is the recursive replacement. This is the power horse in our arsenal. And what it does is we take some input, or as we can see in this slide, we might take only a part of a generalized input. We do extend it because we expect that in front of and behind of a valid element, we can do put other stuff. And yeah, then, as you might have guessed, we insert another generalized input or part of it. We continue extending it so that we can insert even more stuff. And yeah, we actually insert more stuff. And we can keep that going. Actually, in our implementation, we use up to 64 of these steps. And well, for this example, it's only 3, leaving us with a new input that is very different from our original inputs. So the last mutation operation we do use is the string replacement. This one actually does not require our generalized inputs, but we simply replace a keyword by another keyword. And we might end up with evil EAA instead of pprint AA. And this is quite likely to actually generate a lot of new coverage, right? So we have now seen the different mutation operations we do use. And well, the interesting question is obviously, how do they work out? So can we approximate a grammar and do better with our large-scale mutations than the usual candidates, the usual fuzzers, do with their small-scale mutations? And as it turns out, yes, we can. We do outperform AFM, QSIM, Angora on almost all targets that we have tested. As you can see, for Lua, this is not the case. There's the interesting fact that Lua does not only accept source code, but also bytecode, as you might be aware. And that's probably, at least we guess so, the reason that Angora was it? I believe outperforms it there. Anyway, our large-scale mutations are effective, outperforming the small-scale mutations in most cases. The next interesting question is, how do we fare against a grammar-based fuzzer, right? So we are approximating a grammar. It's only fair to see how a fuzzer really working with a grammar performs against us. And unfortunately, from our point of view, the grammar-based fuzzer outperforms us, and often by quite a lot, which is not that surprising because the grammar-based fuzzer has access to the grammar from the beginning on, right? We only start learning, approximating the grammar when the fuzzing process starts. So the grammar-based fuzzer outperforms Grimoire often. Actually, there's one case where this wasn't the case, but in a general case, we are outperformed. So the question is Grimoire of any help when we do have a grammar, right? And actually, it is. What we did is we ran the grammar-based fuzzer for 24 hours, taking the inputs it found as seed, continued running the grammar-based fuzzer, and compared it to Grimoire. So basically, we allowed Grimoire to access indirectly the grammar. And as you can see, Grimoire finds more than the grammar-based fuzzer, which I consider quite cool, to be honest, because we might find elements that are not covered by the grammar, or the implementation may differ from the specification. So, let me conclude this introduction to Grimoire with following. We have seen that fuzzing structured inputs is possible, but small-scale mutations such as employed by common fuzzers such as AFL are not the best for this task. Luckily, we have large-scale mutations from grammar-based fuzzers. However, the grammar must be human-made, and that's what we want to avoid. Therefore, we have created Grimoire, where we can learn the structure of the input, and based on this knowledge, can create such large-scale mutations. And yeah, actually, this has real-world impact too. We found 11 CVEs. So thank you a lot for your attention, ladies and gentlemen. I'm happy to take any questions.
Perfect. Questions?
Hi. So two short questions. First,
Sure.
For the keywords for the string replacement stage, did you have any dictionary involved there?
Yeah. So we do a static strings pass over the binary, extracting the keywords. However, in our evaluation, every fuzzer had access to the same dictionary, so we gave AFL and the others the dictionary too.
Okay, and the second question, what was it? Oh, the tokenization. So how did you determine the optimal length of the tokens? Because like ultimately optimal length would be just one character.
Yeah, so actually we try each power of 2, starting with the size of 256, going down to 1. We try to remove as much as possible. And if that doesn't work out, we try smaller sizes.
So did you see the performance impact based on the length of the token?
No. I can't say much more on that. I'm sorry. Any other questions? Everyone is ready for the pool.
Then, okay, go ahead.
There's one question.
Brave.
Yeah, this conference is so nice. I don't want it to end so quick. So, again, during the tokenization, do you encounter cases when you have to modify multiple parts of the input in order to make a change?
Yeah, so that's actually a problem. So think of XML tags, right? You have the opening tag and the closing tag. Right now, this is not properly detected. We assume that can be fixed by some heuristics. However, currently we do not handle this. That's a good question.
Thank you.
Yeah,
Okay.
that was also the question I had on, as my backup. Like how you could extend this to do some actual grammar synthesis that can be maybe not correct, but at least useful for fuzzing for different kinds of dependencies. For example, the if then else clause that you displayed is kind of similar because some tokens depend on each other.
Yeah, that's actually hard, but we can heuristically try to remove elements and always rely on the new coverage comparing to see whether we actually can remove two elements and they belong together.
Okay, cool. Thank you very much. Let's thank all the speakers together.